Do you know why many game developers are bold? Because they never learned how to debug in time. Today we're going to take care of your hair. I cannot promise it will grow back, but I can help you keep what you have. You're going to learn 3 core skills that every serious programmer and game developer needs. First, how to debug your code with breakpoints and stepping inside Visual Studio so you can see your program run line by line and spot exactly where it goes wrong. Second, how to use assertions to protect your logic and catch broken assumptions the moment they appear. And third, how to use exceptions with try, catch, and throw to handle expected problems in a clean and controlled way instead of letting them explode somewhere else in your code. These tools turn random crashes into clear solvable problems, and they will make every future C++ and Real project much easier to build and maintain. Before we start, help me win the heart of YouTube's algorithm, if it has one. Like the video, subscribe, ring the bell so you do not miss new C++ and Unreal Engine tutorials. Leave a comment and share this with one beginner who might be struggling today. And thanks for that support. Now let's jump into the error handling. Why error handling matters. Before we touch any technical detail, I want you to understand this idea. Errors are not your enemy. They are path to clarity. In programming, we deal with 3 kinds of problems. 1. Syntax errors. This happens when your code cannot even compile. 2. Runtime errors. The program compiles but crashes or behaves in unexpected ways. 3. Logic bugs. Everything runs, nothing crashes, but the result is totally wrong. Every bug you find will fall into one of these. And the faster you identify which type you are dealing with, the faster your solution arrives. Think about the game development. The screen shows nothing. The character does not move. The AI behaves like a drunk robot. All of these are different types of errors. Error handling gives you control. And when you have control, development becomes a creative process instead of a painful struggle. Let us start with the simplest form of debugging: reading compile errors. When the compiler says something failed, always read the first error, not the last. Check the line number. Read the message slowly. It usually tells you what you did wrong. A missing semicolon, a wrong type, a name that does not exist. Do not panic. Treat compiler errors as a feedback. They are teaching you how C++ thinks. Let's do something very simple. X equals 20, integer y equals, let's say, 30, and we're going to remove the semicolons. And here, let's say, std cout the addition of these 2. If we try and run this, you will see there were build errors. Would you like to continue? I always say no. And I try to check on the button what are the errors. And look how simple it is. It immediately tells me that we have a semicolon that I missed. So you can check where it is, the underline in red, and fix it with the semicolon. And if you tried it to run it again, the same error will be presented. And then they can tell you something like this. Look that in the line 9, which is where the integer y is defined, it says syntax error, integer should be preceded by a semicolon. So this integer should be preceded with a semicolon in the previous line. Let's place the semicolon. And now run. There is no error now. Another simple and powerful tool for debugging is print debugging. In this case, you are presenting messages to help you understand where your error could be. Let's say that after we define the values of x and y, I decided to add, let's say, 10 for x and for y add 20. And let's say that we call other methods in other places and make other changes to these values. And that is probably generating some undesired behavior on my program. In that case, I probably want to see the values of these variables at the moment that I'm running the program. So a good example of a print debug could be std cout and std for y. Let's say this is the current x and this is the current y. And if I run my program, then I can see what are the current values of x and y that will generate the result of 80 when I add them. For example, when you are working in video games, you will find in many occasions that you are not certain about a value or something that is happening, and in that case, you use the pre-debugging to let you know on the screen what is happening. The next debugging method is breakpoints and stepping. A debugger allows you to pause your program at any moment and look inside. You place a breakpoint on a line. When the program reaches that line, it stops, and then you can step over the next line, step into a function and see what happens inside it, step out of a function and return to the caller. You also get access to all the variables and their values at that moment. You can see the call stack. You can follow the exact path of execution. When something looks wrong, use this process. 1. Reproduce the bug. 2. Place a breakpoint before the suspicious behavior. 3. Step line by line. 4. Watch how values change. 5. Find the first moment the value becomes incorrect. That moment is your real bug. I am going to take this example and add a new line of code. In fact, a couple. First one, I'm going to define z equals to 0. And now at the bottom, I want to say that integer result is equal to y divided by z. Because we're dividing by 0, this will generate an error. It will crash our program. Let's test it. You can see that the compiler didn't present any error, because in terms of compiling, the code is perfect. But we pass a value which is 0, and that is crashing our program. Look, the message is presenting an error handling exe, exited with code, that code. This is the perfect case to use breakpoints, because let's say that at some point you forgot that this value is 0, and you really don't know where the error is happening. So to start this process, first, be sure that you stop the program. And now let's start setting a breakpoint. Let's say that I want to set a breakpoint on line 10. Then move your mouse to the left margin of the 10, even more to the left. And you see this point. Click on it. You will see a red circle appear. This is your breakpoint. The next step is start debugging. For debugging, you won't use this button because this is for start without debugging. For debugging, you can use this button that says Local Windows Debugger, or you can go to Debug, Start Debugging. And of course, you can use F5 as well. Let's use F5. Now let's move to one side, this section, and you can see that the program stopped in line 10, which is where we set our breakpoint. Visual Studio highlight that with an arrow, a yellow arrow, which means this is the next line of code that we'll execute. Now we can start inspecting variables. You just have to move your mouse over any variable and you will see the current value. For example, x is 20, y is 20. But look, if I move forward, you will see that if I inspect the x here, it still has the value of 20. If I inspect the x here, it still has the value of 20. Why? Well, because the code has been executed until this point. We haven't added the 10 to the 20, which was the original value of x. You can also go to Debug, Windows, Watch, and select Watch 1. A new window will be open on the bottom. Now I want to inspect a specific variable. Let's say x. You can see that now I have the value of x at the bottom. I don't have to inspect it directly with the mouse. Let's add also the y, and why not the z. Now you're starting to using the full power of debugging for Visual Studio. Before we continue, let me share something important with you. This channel is part of a bigger experience called the Game Creator Accelerator Lifetime Mentorship. The goal is simple: a measurable transformation into a game developer with the proof, strategies, and community to build a successful career from there on. You and I work together to build your first playable prototype in Unreal and understand the core principles you will reuse in every future project. We also set up your social platforms so studios, publishers, headhunters, and gamers start noticing and supporting your work. Then we design daily routines and strategies that keep you inspired and moving forward, even after your regular job hours. This is the same approach successful independent creators use to turn small projects into real opportunities, myself included. It helps you start shaping a business model around your learning, while also positioning yourself for studio roles if that's the path you want to take. Because in today's industry, sending applications is not enough. Learning and creating games in isolation is not enough. You hack the system by showing consistent progress, sharing what you create, and letting studios and players come to you. And inside the GCA, we have the methodology to help you do exactly that. But also, with the GCA, you are not doing this alone. You build your own brand, you join a focused community, and you have my direct support, including one-on-one sessions week after week, plus lifetime access to new strategies and weekly reviews. If you want to know more, check the link in the description. Visit Woolon.com, read about the Game Creator Accelerator Lifetime Mentorship, and book a call with me. It will be a game-changing conversation. The next thing is to start stepping through code. Now that your program is paused and you have these variables set that you are inspecting, you can control the code one line at a time. The main stepping commands are step over F10, which executes the current line and moves to the next line. This is great when you do not want to enter inside a function. You just want to step over that step because you know that your function is working and you don't want to waste time on it. Then we have the step into F11, which goes inside the function on the current line. This is opposite to the previous one, and is perfect when you want to inspect the logic inside a function. Then you have step out, Shift F11, finishes the rest of the current function and returns to the caller. This is useful when you went inside the function accidentally or if you inspect whatever you want in the function and you want to continue to the next line after the call to that function. And continue, which is F5, which runs the program until the next breakpoint or until it finishes. In this example, at this point, I want to step over, so I'm going to use F10. Look that now I move to the next line of code, the 12. Nothing is happening, perfect. Let's go F10 again. One important thing, look that the value of x changed to 30. Originally it was 20, but now we added 10, so it changed to 30. Look what is going to happen when I step over also again with y here. Now it is 50 because we added 20. And we are in the next line, which is the 14. Now let's go F10 again. The exception unhandle. Now we know where the error is. We can use also tools like Copilot to help us solve the error. But at this point, we know the reason. It says integer division by 0. Pretty simple, and now I know where is the error and how I can fix it. So I close this, stop my program, and I'm going to fix this value of set. And instead of 0, let's divide by 2. And I want to do something else. I want to create another breakpoint for the line 14. Let's do a local Windows debugger process with F5. We stop in the breakpoint on line 10, and let's say I want to continue to the next breakpoint where I knew that the error was originally there. If I want to jump from this breakpoint to the next one, I just press F5 again. I jump to the next point, and if I want to continue the entire process, now I can press F5 again. Let's check here, and the entire program finished running, and you will see the 30, 50, and the sum. Perfect. Now let's do some changes here. I'm going to cut, in fact, all this section because I want to create a function void, let's call it addition, where I'm passing a and b as integers, and I'm going to present the sum of these values. And after that, I will create another function to present a successful message. Success message. And let's say that that message is operation completely successfully. And I will add another line, which will be something like good job. Let's say good job. And now from integer main, I will call first addition, where I'm going to pass X and Y, and inside addition, I also going to call success message. So this cycle is pretty simple. I will assign these values to these variables. Then I call the function addition. Addition will add these two values and present it on the screen, and then we'll call a success message inside addition. And finally, after I call the addition inside main, I will add another cout to tell something like this is over. I will remove these breakpoints that I don't need, and instead I will set a breakpoint in line 29. Now let me show you the differentiations when we are debugging. At this point we are in the line of the addition. And as I mentioned to you, if I click F10, I will move to the next line without getting inside the addition. Now let's do it again. But this time, instead of using F10, which is a step over, let's use F11. Now I get inside the function addition, and I can use now F10 to step over the different steps on this function. Now let's say that I reach success message, but I don't want to get inside success message. Then I can do F10 again to step over. Look that we move to the next point. And now I will continue in the integer main to the line 30, where it presents this is over. Let's click F5 to continue until the end, and this is the message of my program. Now I want to do something called the check of the call stack. If your code calls multiple functions, the call stack shows you exactly who called who. Let's go to Debug, Windows, and select Call Stack. Now let's click F11, and you can see how these calls are stacking one over the other. Look that we have main, addition, and if I continue this process and get into success message, now you have main, addition, success message, and now let's say that I continue the process. The stack starts to removing the last element, and now again we're back into main. Now let us go deeper into one of the most powerful tools you can use while learning C++, the assertions. Assertions are not fancy. They do not require extra setup. They do not even run in the final release version of your program. But they will save you from hours of frustration because they expose wrong assumptions immediately and clearly. Let me show you how they work and why they matter. But first, let's ask the question, what an assertion really is. An assertion is a simple question you ask your program while it is running. You're basically saying, at this point in the code, this condition must be true. If it is not true, stop everything because something in my logic is wrong. That's it. Assertions are guardrails that protect your own thinking while you write code. To use them, first you have to include the assert. Include C assert. And then you write an assert like this. Let me go to the main. Assert Z is different than 0. I'm sorry, I forgot an R. Assert Z is different than 0. This ensures Z is not 0 to avoid division by 0. If the condition is true, nothing happens. If the condition is false, the program stops and tells you exactly which assumption was violated. So let's start first this scenario. Everything worked smoothly. Now let's move Z to 0. Let's run. We have an error, and you can see the assertion that failed. Z is not different to 0, and it's telling you even the line where this happened, which is the line 29. This assertion is not working. The assert does not fix the error, but it points you directly to the source of the bad logic. For your scenarios, maybe you calculated damage incorrectly. Maybe a healing function doubled the value. Maybe something became negative without you noticing. Without an assertion, this bug might hide for hours. And with the assertion, you find it instantly. Just click here to stop it, and now you can make your fix. This is the best part of assertions. Assertions only run in debug mode. When you build a final release version of your program or game or application, all asserts are removed automatically. So you can fill your code with as many sanity checks as you want without affecting performance or players. Assertions are pure development tools. Now let's move into another subject of debugging, which are the exceptions. So far we've seen compiler errors, runtime crashes, and logic bugs. Exceptions are another tool in your toolbox. They give you a controlled way to say, something unexpected just happened, and we need to stop the normal flow of this function. Instead of letting your program crash in some random place, exceptions help you stop exactly when the problem appears, and then react in a clean and structured way. Here's a mental model I want you to have. You are inside a function. You detect a problem that you cannot or should not handle here. You throw an exception. The normal execution stops. C++ starts looking for a place in the call chain that can catch and handle that problem. If C++ finds a matching catch block, your program can recover or at least print a clear message. If nobody catches it, the program terminates. That is still better than silent bug that corrupts your data without warning. Let's create an example to show it. First, we need to include the std_except. Now let's create a function. Let's call it integer save divide. In that function, we're going to pass two values, one for the numerator and the other for the denominator. If denominator is equal to 0, you throw an exception. It can be an invalid argument, but you also have other options. It can be a runtime error. In other words, here we're saying if denominator is 0, something is wrong. We cannot return a valid result. So we throw a standard invalid argument error with the message that says denominator cannot be 0. Another usual standard error could be throw std runtime error division by zero. This is a more generic type. I'm going to comment the previous one, but now let us see how to call this safely. Let's go down again to the main, and after all the things we did, let's add something called try. Try is the way that we use to catch an exception. The try has two sections, one that is the try and the other that is the catch. Let's say that I want to obtain a value which is the division result of x and z. And of course I want to present the value of the division. But because in save divide I define a way to handle exceptions, I also have the possibility of calling the catch and present the exception. What was the reason that generated the error? And as you can see, the syntax is pretty straightforward. In the catch, you define a const runtime error and pass as a reference the E. And then you can present the C error. You can also use C out. And from the E, you will get the what. What was the cause of this error? Right now, Z is equal to 0, but we have the assertion here. So at this point, I'm going to comment out these two lines. And now let's run. The first part executed, but then we have the error division by 0 error, which is this exception that was executed at this point, because the denominator is equal to 0. Now, what is actually happening? What is the flow of control of when we throw an exception? First, the current function stops right away. Second, local variables in that function are cleaned up. 3, C++ walks up the call stack, function by function, looking for a catch that matches the type of the exception. 4, the first matching catch block is executed. And 5th, if no matching catch block is found, the program terminates. So you can think of it like a signal that travels up the call chain until someone says, I know how to handle this. You might be wondering what tool to use in which situation. Here's a simple guide while you are learning. Use simple return values and if conditions for normal everyday errors like invalid user input. Use assertions to catch mistakes that should never happen if your code is correct. Use exceptions when something unexpected happens during execution and you want a clean way to stop and report the problem. This balance will serve you well not only in this course but also when you start developing games with Unreal. Now you understand the fundamentals of error handling. You know how to read compiler messages, how to debug your code step by step, how to protect your assumptions with assertions, and how to work with exceptions using try, catch, and throw. These tools will save you hours of frustration and transform you the way you think about your own logic. Help me beat the algorithm and grow this channel. I am trying to convince the algorithm that game dev education matters. Like the video, subscribe, leave a comment with your next question, and share this with one beginner who could use some support. And if you want to start a measurable transformation into game dev after office hours, visit woolen.com to learn more about the Game Creator Accelerator Lifetime Mentorship and set a time to chat with me one-on-one. Until next time, keep creating, keep sharing, and most importantly, keep dreaming big. I'll see you soon, my fellow creators.